We humans noticed it quite early, the universe. Of course, there were fixed stars in the sky, but there were also other stars that were continually shifting their positions while chasing one another along a celestial path that appeared to have been constant over the ages. Before it was understood that our star was stationary and that the Earth was rotating together with all the other known planets, this path was also followed by the Moon and first appeared to follow the Sun. In essence, what the ancient watchers were seeing was unusual. While the wandering stars, or planets, appeared to be obliged to move all inside that extremely thin, imaginary band that encircled the entire celestial sphere, the fixed stars covered the sky throughout and were free to shine wherever they pleased. The so-called zodiac belt, in which the 12 constellations that the planets, Sun, and Moon cross, was immediately associated with the belt that became known as the ecliptic, since only along its route could an eclipse between the Sun and Moon occur. Since it was evidently infused with meanings connected to astrology and divination depending on the location of the stars, the ecliptic was of enormous interest to early sky watchers. When astrology's mysticism gave way to science, it became obvious that the ecliptic did have significance, but it was only astronomical in nature. As Kepler's laws and Galileo's telescope definitively proved the nature of the wandering stars, it all of a sudden became obvious that the planets orbiting the Sun in the same plane could not be a coincidence. Since gravity, the force that keeps the planets in these stable orbits, operates the same manner in all three dimensions, it is really predicted that the orbits are randomly oriented. Since someone took the time to calculate that the odds of having a solar system with 8 planets orbiting such similar planets are about 1 against 30 billion, it would have been more normal to observe an arrangement more like that of a swarm buzzing around a beehive rather than a nice, orderly series of nearly perfect circles. It was obvious that the explanation for that peculiarity had to do with the solar system's genesis. But specifically from what? This question has a complicated answer that incorporates a number of crucial physical ideas that we are about to study together. Are you prepared to travel through billions of years in the past? The solar system, which we now believe to be our celestial home, was ready to take shape long ago, when the Milky Way's pace of star formation had virtually reached its maximum. This was pretty usual for those times, but it also meant something very special for us. A structure that, as we shall see, would endure for millions of years rather than just a day or even a century. The length of time it took for our sun to form and start out its main sequence life. In a human timescale, 10 million years may seem like an endless period of time, but in reality, they only account for 1,000th of the universe's total age at the moment. The processes we are about to describe, however, are all extremely slow and vast in scale. Our most devastating earthquakes and tropical cyclones are in no way comparable to the phenomena we are about to describe. Among the dim veils of a cloud lazily orbiting 27,000 light-years from the galactic center, our story begins 4.6 billion years ago. By human standards, it is a massive gas cloud that spans 50 to 100 light-years, despite its size is merely 1,000th of the galaxy's total diameter. Its temperature is extremely low, only a few degrees above absolute zero, and its density, which is generally 100 molecules per cubic centimeter, could approach the most driven vacuum we now experience on Earth. The genesis of our solar system is fully located in this frozen cosmic emptiness that is currently floating in total darkness. This may seem unusual. A scenario so gloomy that several paragraphs from The Black Cloud by Fred Hoyle come to mind, if not even the verse from Genesis that reads, "Darkness enveloped the abyss and the Spirit of God hovered over the seas." But, as the focus of this movie is astronomy, we must state up front that the Spirit of God was actually made up of 73% molecular hydrogen and 25% helium, with just 2% of the other components being carbon, nitrogen, oxygen, and silicon compounds, as well as thousands of additional nebulae that at the time covered the galaxy's disk. Higher density areas of the cloud started to collapse due to gravity at some point because something disturbed the cloud's otherwise peaceful state. The most widely accepted hypotheses suggest that this something might be one or more supernova explosions, shock waves caused by radiation from nearby newborn stars, or a close collision with a giant star. In actuality, the cloud is in a state of dynamic equilibrium between the force of gravity, which seeks to keep the particles close together, and the thermal energy of its particles, which tends to scatter them. The force of gravity may triumph over internal pressure in some areas of the denser cloud if this equilibrium is disturbed by internal turbulence or an external factor, leading to instability that could result in the formation of something completely different from a cool cloud of gas. Whatever its source, the perturbation's effect is to thicken and divide the cloud into hundreds or maybe thousands of tiny globules, each measuring approximately 1/10 of a light year and being more than 100 times larger than the solar system as it is at the moment. And after that, a star will be born in each of them. It is important to understand that stars do not form in isolation, but rather in groups of hundreds of stars. Gas continues to collapse within the globule that most interests us, obviously the one in which the sun is forming, and the denser region heats up, while a kind of dusty cocoon forms around it from the material of the primordial cloud that has not yet been involved, atoms, molecules, and dust made of heavier elements. The globule's core gradually starts to condense and exhibit a more pronounced spin. In actuality, not all areas of the cloud experience the collapse at the same time or with the same intensity. The initial cloud is so big that it allows varied dropping speeds in each of its areas, which causes a favored rotation to occur at some point like a downward air current. The cloud thus starts to whirl and compress at an ever-increasing rate. The crucial concept of conservation of angular momentum, which states that in the absence of outside forces, the quantity measuring how strongly a body rotates about its axis does not change over time, governs this occurrence. Do you know what an ice skater is? She accelerates her rotational speed while maintaining constant angular momentum as her arms get nearer to the body or to its axis of rotation. Hence, even though our primordial cloud had a relatively slow initial rotation, it speeds up as the material gets denser and the volume gets smaller. The matter does not all fall toward the center, where the sun is to be lit, due to the centrifugal force caused by the revolution. Instead, some of it spreads outward and forms an accretion disk with a radius of at least 100 astronomical units. Collapsing and aggregating thus form the so-called planetesimals, solid bodies of a few kilometers in size, which in turn give rise to the protoplanets, that is, the progenitors of the planets we know today. The latter then fragments into smaller parts, each of which begins to collapse and rotate on itself independently, taking with it some of the overall initial angular momenta. This is the overall picture, but several elements of the problem require considerably more clarification. What exactly do we mean when we state that the planets orbit the sun in a roughly common plane, for instance? Actually, there is some misalignment since, in absolute terms, the difference between the highest and least inclined orbits is only 6 or 7 degrees. The precise value of this discrepancy depends only on the reference system we use to measure it. And here we see that the ecliptic line is not only wholly fictitious, but also only a convention. In actuality, the ecliptic plane is nothing more than our planet's orbital plane. And we start figuring out the inclinations of the other orbits from this fictional plane. This means that by definition, the inclination of the Earth's orbital plane is 0 degrees. Mercury will be 7 degrees, Venus's is 3.40, Jupiter's 1.3, and Mars 1.85, Saturn 2.5, Uranus 0.77, and Neptune is 1.77 degrees. Alright, but given that they do not reflect a reality based on the physics of planetary formation, we simply employ these values for computational convenience. Actually, as Earthlings like to be at the center of every measurement and calculation, we are only discussing a pure convention. Things would alter significantly if we calculated the inclinations of the orbital planes on the equatorial plane of the Sun. In actuality, the Sun's axis of rotation is clearly inclined rather than perpendicular to the planet's orbital planes, as one might anticipate. Nobody had presented a strong justification for this departure up until this point. Perhaps an answer might be forthcoming thanks to the fictitious presence of a massive planet that some astronomers think might revolve around the Sun at a distance of a few hundred astronomical units, tilted 30 degrees. In essence, what is now commonly known as Planet 9, and which astronomers have been searching for since early 2016, when its existence was hypothesized based on gravitational anomalies observed for objects beyond Pluto, may have had an impact on the configuration of the orbital planes of other planets over the course of billions of years. As a side note, we were claiming that everything would change if the orbit's inclinations were determined in relation to the Sun's equatorial plane. The Earth's orbital plane would incline the greatest, by 7.1 degrees. Mercury's would be 3.4 degrees, Saturn's 5.5, Venus 3.9, Mars 5.7, Jupiter's 6.1, Neptune's 6.4 degrees, and Uranus is 6.5 degrees. It's really odd, isn't it? The huge satellites of gas giants, for instance, which nearly exactly lay in the plane of rotation of the planet to which they belong, are an example of celestial objects generated in accretion disks. Of course, all of this also applies to planets and other celestial objects. Then there are smaller bodies, like asteroids and comets, which exhibit extremely high orbital inclinations under the most extreme circumstances. Similarly, consider the dwarf planets Pluto and Eris, which, despite being sizable, orbit at an angle of 17 degrees and 44 degrees, respectively. Evidently, the gravitational destinies or births of each object were quite different from those of their larger siblings.